Welcome to my video lecture. This is Amarnath under the course Linear Algebra and Calculus. Today I am teaching diagonalization of a matrix. It is a continuation to the previous topic, Cayley-Hamilton theorem. Let us see the today's topic. Right. In the last class, we have discussed about the Cayley-Hamilton theorem last two videos and there its applications and especially polynomial problems we have done. Now, in addition to the Cayley-Hamilton theorem, now we are going to learn how to diagonalize a given matrix and what are the advantages of the diagonalization called applications. Okay. So, let us do this diagonalization of a matrix. So, here let us first discuss about the definition of the diagonalization. See, a matrix A is diagonalizable if there exists an invertible matrix, especially they are saying invertible matrix P such that P inverse A P will become diagonal matrix. So, here we are taking a matrix P such that P inverse AP will become a diagonal matrix. So, what is the P and how to do the diagonalization? Let us discuss. So, where D is a diagonal matrix. What do you mean by diagonal matrix? Diagonal matrix means where the principal diagonal elements will be D1, D2, D3 and other elements being 0. Let us say if I take 3 by 3 matrix, it is a diagonal matrix. Except the principal diagonal elements, other entries will become 0. So, for any given matrix A, some matrix A will be given, that will be a, let us say 3 by 3, 2 by 2 or n cross n. How to convert into a diagonal matrix we are going to discuss. This matrix A will be converted to diagonal. What is the matrix A here? A11, any matrix A12, A13, A21, A22, A23, A third row A31, A32, A33, any matrix given square matrix, especially 3 by 3, 2 by 2, 4 by 4. So, how to convert a diagonal matrix? This transformation is very useful in so many problems. So, our topic is diagonalization. Now, here let us here small note point before going to the topic. N cross n matrix is diagonalizable if and only if it possesses a n linearly independent eigenvectors. The meaning, if 2 cross 2 matrix is given, then you have to get 2 eigenvalues and corresponding 2 eigenvectors and 3 by 3, 3 eigenvectors. Suppose n cross n matrix is given, then we must get n eigenvectors that are linearly independent. The one eigenvector should not depend on the another one, that are called linearly independent eigenvectors. Let us take some examples. Suppose x1 is equal to 2, 2, 2. Let us take x3 is equal, x2 is equal to 4, 4, 4, 4. See, let us see these two are independent or dependent. See, so x2 can be written in the terms of x1. x2 is equal to 2 into x1. See, means x1 and x2 are linearly dependent, not independent. So, such type of eigenvectors are should not exist. So, as per the statement here, theorem statement, I am giving as a note point. So, if it is n cross n matrix, you have to get n linearly independent eigenvectors. Then only diagonalization is possible. Suppose if we don't get n number of eigenvectors, the given matrix cannot be diagonalized. That we clearly discuss in the next video lecture. Today we discuss about the matrices which can be diagonalized. Right. Now, so here the definition, what is the key point to be remembered here, that is P inverse AP is equal to D, which is the formula for diagonalization. Then what is P, what is D? D we discussed, that is a resulting diagonal matrix. Then what is the P means, that is a model matrix. So, here I am giving in the next class definition. Now, let us look at the definitions. Model matrix and spectral matrices, right. So, in above diagonalization process, what is the diagonalization process? P inverse AP is equal to D. I am giving the formula as the diagonalization. In this diagonalization process, the involved P, right, is called the model matrix. The P matrix is called a model matrix and D matrix, the resulting matrix, is called spectral matrix. Then what is the model matrix consisting? So, the model matrix here, that consisting of the eigenvectors which we obtained for the given matrix. So, the model matrix consisting P is equal to eigenvectors x1, x2, x3, so on. It is a n cross matrix, then it will contains n eigenvectors, that too linearly independent eigenvectors, that is the model matrix P. So, for every problem we are getting the eigenvectors. So, first eigenvector is the first column, second eigenvector is the second column, third eigenvector as the third column. If you write all the eigenvectors in the columns, the obtained matrix P is called model matrix. In the process, what we are getting the D, diagonal matrix. D is called the diagonal matrix, that is spectral matrix. So, two things in the P inverse AP is equal to D. P is called a model matrix, the result matrix D is called spectral matrix. D, just now we discussed what is the diagonal matrix, right. Generally in this process, P inverse AP is equal to what we get in the process here, P inverse AP is equal to D. Here P, which is a model matrix, and D consisting the diagonal elements, especially eigenvalues in the diagonal, lambda 1, 0, 0, so on. So, 0, lambda 2, 0, 0, so on. So, here n cross n matrix 0, 0, 0, the last element will be lambda n. Exactly in the principal diagonal, we will be getting eigenvalues as the diagonal elements, that is a required diagonal matrix. In above diagonalization process, the final result D will contains like this. So, let us explain the procedure, how to find the eigen values and eigenvectors. We have discussed very clearly in the previous topics. Now, using eigenvalues and eigenvectors, we are going to do this diagonalization procedure. So, diagonalization process. Let us discuss what is the algorithm or the step-by-step procedure to find the diagonalization of a given square matrix. Let us see the procedure, right. So, let us say given matrix, so square matrix, let us given square matrix, given matrix n cross n, that we are calling as a square matrix, for which square matrix A, that we are going to diagonalize. We are going to transform the matrix A to a diagonal matrix, right. So, the P inverse AP we are calling as the diagonalization procedure. Then, how to diagonalize the given matrix? So, exactly point of the exam that I am teaching here. Now, for the given matrix, we need to find eigenvalues and eigenvectors. Using the previous lectures, we have clearly discussed how to find eigenvalues and eigenvectors of the given matrix. So, first step, our first task is to find eigenvalues and eigenvectors. Of given matrix. So, it is a 2 by 2 or 3 by 3 or for a given matrix, we are finding eigenvalues and corresponding eigenvectors. We know very well how to find the eigenvalues and eigenvectors, right. Next, form model matrix. What is the model matrix? Just now we discussed, that is P, which consisting the eigenvectors, whatever the eigenvectors you determined, write in the matrix P, x1, x2, x3. Let us say I am explaining for 3 by 3 matrix, let us say only taking 3 by 3 matrix, this is x1, x2. So, let us discuss about for restrict for 3, it is 2 by 2, 2, n by n, n. So, I am taking a 3 by 3 matrix, the model matrix will consisting 3 eigenvectors, that too linearly independent eigenvectors. Suppose dependent eigenvectors are there, we cannot diagonalize. Next, after getting the model matrix, so the diagonalization. So, P inverse you find, P inverse. What is the P inverse? 1 by det P into adjoint P. This is a formula for finding the inverse of a matrix. So, since you have formed the model matrix, find the inverse using this formula, or in using scientific calculator, we can find the inverse of a matrix. Take a mat A matrix and enter the 3 by 3 and enter the values, and you can go for mat A inverse. That can be done very easily in the scientific calculators. Since the students are allowed to use the scientific calculator, they can find the inverse of the matrix using the scientific calculator. So, we find P inverse. Next, fourth one. So, the diagonalization process. So, the diagonalization formula. What is the formula? P inverse AP is equal to D. This is the formula to find diagonalization. So, P inverse already we got. A is the given matrix, P is the model matrix. The what will be the resulting matrix? That will be the D, which is contains only eigenvalues in the principal diagonal. So, P inverse we have, and A is the given matrix, P is the model matrix, right. So, these three you have to multiply. So this is P inverse, this is a given matrix A, and P is the model matrix. We have all three values. You can multiply these three and the resulting value will be the diagonal matrix that contains eigenvalues 0, lambda 1, 0, 0, second eigenvalue lambda 2, 0, 0, lambda 3. These are the final output this will be. So this how to multiply these three matrices? First you multiply first two matrices, then third matrix. Otherwise you can use scientific calculator. So this one you can enter in mat A, this one you can enter in mat B, you can enter in mat C. So since matrices multiplication associative, you can multiply three matrices at a time. So mat A into mat B into mat C, definitely we will be getting exactly in the diagonal eigen value. That is nothing but which is a diagonal matrix. So it is a very clearly diagonal of eigenvalues lambda 1, lambda 2, lambda 3. So in the diagonal it contains the eigenvalues. That will be the procedure. Very simple. Just find eigenvalues and eigenvectors. We are very familiar how to find eigenvalues and eigenvectors. Then using eigenvectors form the model matrix P, which contain all eigenvectors. So first eigenvector, second eigenvector, third eigenvector. The three together will form the model matrix. But you need to confirm that three must be linearly independent eigenvectors. Then find the P inverse. How to find P inverse? The formula is 1 by det P adjoint of P. Otherwise, we can use the scientific calculator and we can find the inverse of the P. Now, we need to show diagonalization. That is the formula P inverse AP is equal to D. Since we have P inverse and A and P, multiply these three matrices, exactly we will be getting a diagonal matrix. That too especially it contains eigenvalues in the diagonal. Remaining elements, so other than these 6 elements will be 0. The same procedure can be done for 2 by 2, 3 by 3, 4 by 4 or n cross n. This is the diagonalization procedure. Right, let us explain the diagonalization with an example. But before that, here we have one application also, that is a calculation of powers of a matrix. Means we can find a power n powers at example, that is you can find a power 4, a power 5, higher powers, a power 6. In the Cayley-Hamilton theorem also we have discussed how to find the higher powers of a matrix, right. So here also we have the application, we can find the higher powers, a power 6, a power 7, a power 8, nothing but a power n. That is using diagonalization. So we have the procedure diagonalization P inverse AP is equal to D, right. Now again I am multiplying P inverse AP into P inverse AP. Just I am going to derive the formula for calculation of the powers P inverse AP into P inverse AP, which is equal to D into D, right. D into D, that is D's, let us write here now. So since matrices multiplication is associative, right, we can write P inverse A into P inverse. How can I write like this? Because matrices multiplication A associative, A B into C is equal to, you can write A into BC. This is called associative property. So using that property I can write this product like this. So D into D, D square. Now we know any matrix A into A inverse is equal to I. Similarly P into P inverse also I. Okay. Now P inverse A into I into AP is equal to D square. Now again we know any matrix is multiplied with identity matrix, again that will be same matrix. So here I into this one is again the same result will be there. So P inverse A into I into AP, again you can write AP, which is equal to D square. Now here using associative property, this A and this A can be multiplied, A into A square. So finally P inverse A into A square into P, which is equal to D square. Now I want A power 2, A power 3, A power 4, higher powers I want. So similarly using the same concept we can write P inverse A cube into P is equal to D cube. And again if you multiply one more time with P inverse AP on both sides, you will get, again if you multiply one more time, A power 4 P is equal to D power 4, so on we can get. So finally what I can write here, that is P inverse A power n into P is equal to D power n. continuing the same procedure, and here 2 times multiplied, I am getting a square, 3 times multiplying a cube, 4 times 4, a power 4, n times I will get a power n. Simultaneously, it is the d is multiplied to the right side, that will be d power n, but I want only a power n. Then to cancel this p inverse and p on both sides, multiply with p and p inverse. So post multiply by p inverse, pre multiply by p. So post, right? So I am pre multiplying p into p inverse, a power n, p inverse. So pre multiplying by p, post multiply, pre means before, post means after to the this given term. So d power n also same thing, pre multiply by p, d power n as it is, post multiply by p inverse. Okay, right? Now again we know already, we have mentioned very clearly, p into p inverse is I, a power n, p into p inverse is also I, which is equal to p inverse, that is d power n. Again we know I into identity matrix is any matrix, the product will be same, that is a power n, and when you are multiplying on pre and post here, p inverse. So a power n is equal to p into d power n into p inverse, the final formula to find a power n. So you can put n is equal to 3, n is equal to 4, suppose n is equal to 5, you want to find a power 5, what could be the answer? P into d power 5 into p inverse. Like that, any higher powers you can, d power 5, we may feel d power 5 find it difficult because it is a diagonal matrix, directly you can find the d power 5. So lambda 1 power 5, lambda 2 power 5, lambda 3 power 5, directly we get p. At any cost we are getting the model matrix, p inverse we have, all three we have. So multiplying these three matrices we can get a power 5, not only a power 5, a power 8, a power 10, simply we can get. But actual multiplication, you want to find a power 5, you have to multiply mat a 5 times. So this is one of the application of the diagonalization, we can find higher powers of a matrix. So a power n we can find. So what is the formula to find a power n? P into d power n into p inverse, where p is the model matrix, d power n is a diagonal matrix power n, p inverse is the inverse of the model matrix. So example here I gave how to find a power 5. So this application, let us discuss this diagonalization and how to find higher powers of a matrix using one example, right? Now let us go for the one small problem here. So given matrix A, which is a which order matrix? It is 3 rows, 3 columns. So what he is asking the question here, diagonalize the matrix, hence with the diagonalization procedure, with the result of the diagonalization, you should find a power 4, directly, not multiplying a into a into a into a 4 times, no. So with the result of this one, he is asking, hence then you should find from the diagonalization a power 4. So what is the procedure? We know very well, right? So first step, what we need to find? Eigenvalues and eigenvectors. So right, find, so given matrix A. So find eigenvalues and eigenvectors. Find eigenvalues and eigenvectors. So since we know how to find eigenvalues and eigenvectors, that we will do with the characteristic equation, we know very well. So that is a characteristic equation. What is the characteristic equation? Det of A minus lambda I is equal to 0. This is the characteristic equation. We know very well how to do that characteristic equation. Here we should subtract the lambda from diagonal. 1 minus lambda 1 1, 0, 2 minus lambda 1, minus 4 4, 3 minus lambda. It is called characteristic equation. We know very well how to find the eigenvalues and eigenvectors of the matrix. So by solving this determinant is equal to 0, we get the eigenvalues. So here I am writing what are the eigenvalues here, lambda is equal to solving. So here again I am not going for the complete procedure, directly I am giving the what are the eigenvalues of this matrix, because in the previous lectures clearly we have done how to find eigenvalues and eigenvectors. So for this problem, the eigenvalues are 1, 2, 3. Right? You can check these are correct or not. sum of the eigenvalues 1 plus 2 plus 3, 6, and trace of the matrix 1 plus 2 plus 3, 6 is equal to 6. These eigenvalues are correct. So here by solving this determinant, I am writing directly, and we need to find corresponding eigenvectors to the lambda is equal to 1, lambda is equal to lambda is equal to 6. So these are the required eigenvalues. Next, eigenvectors. What are the eigenvectors? I am taking determined values I am giving here, that is eigenvectors for lambda is equal to 1. I am calling as the first eigenvector. But the first eigenvector here is a 1, 2, minus 2, and the second eigenvector for lambda is equal to 2. That is second eigenvector 1, 1, 0. Third eigenvector x3, which is equal to, here I am taking 1, 1, 1. So here in this problem, I am not finding the eigenvalues and eigenvectors. Directly I am taking as the predetermined values. 1, 2, 3 are the eigenvalues, and for 3 eigenvalues respective corresponding eigenvectors x1, x2, x3. These are the 3 eigenvalues and 3 eigenvectors. So here these 3 are x1, x2, x3 are clearly linearly independent eigenvectors. Without verification, we can say these are linearly. Why? Because eigenvalues are distinct. Whenever the eigenvalues are distinct, we have a theorem statement. For the distinct eigenvalues, the determined eigenvectors will be linearly independent eigenvectors. That is a theorem statement. So even you check also x1, x2, x3 are linearly independent. One vector do not depend on other vector. So clearly x1, x2, x3 are linearly independent eigenvectors. Li means linearly independent. Okay, these are linearly independent eigenvectors. So now first step, the foremost important step in the diagonalization procedure, first we need to find eigenvalues, then eigenvectors. Now using these eigenvectors, we are going to do a diagonalization procedure. Let us go for the next one. Here first we need to form, as per the procedure, here we need to form model matrix P. What is the model matrix P? That is which contains all the eigenvectors as the columns x1, x2, x3. So this is the model matrix P. So what is the model matrix P? First eigenvector, just now we have done first eigenvector which we have given 1, 2, minus 2. Second eigenvectors 1, 1, 0. Second eigenvector second column. Third eigenvector as third column 1, 1, 1. So this is the P. Okay, model matrix means which consisting the all eigenvectors as the columns, right? So this is the model matrix P. Next we need to find P inverse. Find P inverse. Okay, that also I am taking predetermined. P inverse, I said now using scientific calculator we can find, otherwise 1 by det P into adjoint P also we can use. What is the value of the P inverse? Here I am writing directly minus 1, 1, 0, 4, minus 3, minus 1, right, minus 2, 2, 1. This is the inverse of P. You can verify that value. So minus 2 to 1. Now that's our first duty. This is the important one because the total diagonalization happens with the help of model matrix. Now diagonalization. What is the diagonalization? Formula which we have discussed earlier, diagonalization, that is P inverse AP is equal to D. This is a diagonalization formula. So since we have P inverse AP, we can find D, right? P inverse AP. So P inverse we have written minus 1, 1, 0, 4, minus 3, minus 1, minus 2, 2, 1. This is P inverse value. And P means model matrix. What is the model matrix we have here? 1, 1, 1, 2, 1, 1, minus 2, 0, 1. This is a P inverse AP. So here, sorry, here we can write the matrix A, given matrix. Their next step we will be writing P. So A matrix. A matrix means the given problem. This is P inverse and given matrix, that is 1, 1, 1, 0, 2, 1, minus 4, 4, 3. This is a given matrix, right? P inverse AP. P inverse given matrix A and P. Here we have P value now, that is a 1, 1, 1, 2, 1, 1, minus 2, 0, 1. These three matrices to be multiplied. How to multiply? One matrix you enter in mat A, one matrix in mat B, mat C in scientific calculator. At a time you can multiply these three. That will be the resulting matrix. So manually you want to do first two matrices, then with the last matrix you have to do. So since scientific calculator is allowed, we can multiply mat A one matrix into mat B one matrix, mat C, mat A into mat B into mat C. You will be getting the result. So already we discussed here, definitely the D is a diagonal matrix that contains eigenvalues in the diagonal. What are the eigenvalues for this problem? Here we have eigenvalues lambda is equal to 1, 2, 3. These three values only will come in the diagonal, that we can verify on multiplying 1, 2, 3. So other elements definitely 0. So whenever we multiply these three, definitely we get this diagonal matrix. So clearly we are calling as a D, where D is equal to, so D is equal to diagonal of diagonal elements 1, 2, 3, which is a required diagonal matrix. Required diagonal matrix. So he is asking to find diagonal matrix for the given matrix A. So this is a required diagonal matrix. So clearly we got P inverse AP. A is a given matrix. We got the diagonal matrix D. So the major part of the diagonalization is finding eigenvalues and eigenvectors only. Again, and we need to verify that three eigenvectors are linearly independent or not independent. For this problem, the eigenvalues are distinct. So there is no problem. Since these three are distinct, automatically the determined three eigenvectors will be distinct, that are linearly independent eigenvectors. So diagonalization is possible. Right. So P inverse AP is equal to D. And the question second part from this diagonalization procedure is asking to find A power 4. What is asking the here? A power 4, higher power. A power 4 we need to find using this diagonalization. Let us find. Now to find A power 4. So using diagonalization we have the formula. What is the formula? We have diagonalization. A power n is equal to P into D power n into P inverse, right. This is the formula. I want A power 4, put n is equal to 4, right. A power 4 is equal to P into D power 4 into P inverse. Yes, do we have all these values? Yes, we have P value, we have D, we have P inverse, we have. Substitute, that will be the A power 4. A power 4 is equal to P into molar matrix P. What it contains? All the eigenvectors 1, 2, minus 2, next 1, 1, 0, 1, 1, 1. This is the P. In the earlier slide we wrote the model matrix P. Next D power 4. What is the diagonal matrix? We have diagonal 1, 2, 3 diagonal. Remaining element 0, 0, 0, 0, 0, 0, 0, power 4 into P inverse, right. P inverse, what is the P inverse? We got minus 1, 1, 0, 4, minus 3, minus 1, minus 2, 2, 1. This is P D power 4 P inverse. So here no need to simplify this P matrix, as it is you can write 1, 1, 1, 2, 1, 1, minus 2, 0, 1. Now power 4, 1 power 4. This directly we can write powers to the diagonal elements, because in the matrices multiplication we know very well, whenever the diagonal matrix is multiplied, just only diagonal matrices will be multiplied, remaining elements will become 0. So that is directly you can write 1 power 4, 0, 0, 0, 2 power 4, 0, 0, 0, 3 power 4. No other element will get changed. So you can take one example and you can check, right. Minus 1, 1, 0, 4, minus 3, minus 1, minus 2, 2, 1. So the remaining values I am not doing a change. Again, like previous problem, this you enter in mat A, this enter in mat B, you enter in mat C. Using scientific calculator, we can multiply mat A into mat B into mat C. Will give required product. So here I am writing predetermined value, that is the value is minus 99, 115, right, 65, minus 100, 116, 65, minus 160, minus 160, 81. These are the a power 4. So, see, a power 4 means actually we need to multiply a 4 times. So, here you no need to multiply, using the application of the diagonalization we are doing. That is the formula a power n is equal, this is the formula we are writing p d power n into p inverse. P is the model matrix, we have D diagonal matrix, we have P inverse of the P. So, using these 3 matrices we can find any power, not only a power 4, a power 6, a power 8, a power 10, any higher power also easily we can determine just only multiplying 3 matrices. That is the application of the diagonalization, right. So, here I am concluding my lecture. In this video lecture, we have discussed about the diagonalization, how to diagonalize the given matrix with an example we have done, and the procedure for diagonalization, and one application, that is how to find higher powers of a matrix. That is application here we have a power n, how to find a power 4, a power 5, a power 6, that application we have done. So, it is one of the important question in the examination. Using eigenvalues and eigenvectors, we can diagonalize the given square matrix. In the next class, here we are going to discuss about the matrices which cannot be diagonalized. All matrices cannot be diagonalized. I said very clearly, for the given matrix, if you get n number of linearly independent eigenvectors, suppose 3 by 3, you have to get 3 linearly independent eigenvectors, then only we can diagonalize, otherwise we cannot diagonalize. So, we will do some examples which cannot be diagonalized, and how to diagonalize especially symmetric matrices. So far we have done, it is not a symmetric matrix, one small example I have taken, especially for symmetric matrices. A symmetric matrix in the sense A transpose is equal to A, such type of matrices, how to do the diagonalization, that all we discuss in the next class. Okay, thank you.